Okay, let's get started. Welcome back. So we're going to continue on to lecture 7 today, and the topic for today is going to be generative learning algorithms. So the plan for today is to cover Gaussian discriminant analysis, GDA. This is also on your homework, and then move on to naive Bayes, another generative learning algorithm. And before we dive into generative models, let's look at what we've covered so far. So far we have covered linear regression, logistic regression, and generalized linear models. All three of these are what you may call discriminative algorithms. We call them discriminative algorithms because they directly model P of y given x, where y is the desired output and x is the input. Right? And supervised learning, in the supervised learning setting, we are interested in learning mappings from x to y. And when y given x is assumed to be a normal distribution, what we get as a consequence is linear regression. And when y given x is assumed to be Bernoulli, as a consequence we get logistic regression. And when y given x is assumed to be in the exponential family, we get generalized linear models. And we saw that generalized linear models is a broad family, and it includes normal and Bernoulli as special cases. So linear regression and logistic regression are special cases of generalized linear models. And now, we're going to start focusing on x. In discriminative algorithms, x is assumed to be given. In fact, when we were looking at these methods, each of the xj features or attributes could have been real valued, could have been integer valued, could have been booleans, and we were kind of agnostic to it. Right? But now we're going to focus on x, and we will model P of x comma y. Instead of modeling P of y given x, that was the conditional distribution, we're now going to model P of x comma y, that's the full joint distribution. Right? And this joint distribution is also commonly called as the model. Right? And we see that this can be factorized using the chain rule of probability into P of x given y times P of y. Right? And P of y is also commonly called as the class prior. Why is it called the class prior? So we will be focusing mostly on the cases where y is discrete valued, which means these generative models that we're going to discuss today, Gaussian discriminant analysis and naive Bayes, are best suited for classification problems. So y indicates the class of a given example, and P of y is just the marginal probability of y. And the class prior generally, you think of it as what is the fraction of examples which belong to a particular class, without even looking at the x features. Overall in your population, what fraction of your examples belong to a particular class. Right? And P of x given y is generally high dimensional. Right? So P of y given x, in these two examples, y was a scalar. It's either a real valued or a 0 or 1. Right? Whereas generally P of x given y is high dimensional, where x is the set of all your features. Right? And so P of x given y, we are trying to model a high dimensional probability distribution because your features can be very high valued, and that's in general a harder problem. High dimensional probability is in general harder both for analytical and computational reasons. Yes, question.
So whenever you have a model, the plan gives you the training data, the plan gives you the test that you want to test on. Why would we account for the probability of occurring of x?
So the
Take x as a given.
Right. So the question is, why do we want to do generative modeling? Why do we want to model P of x? Because x is generally given to us. Is that the question? Yeah. So there are a few reasons why you want to do this, and we will touch upon that towards the end of Gaussian discriminant analysis. At this point, we will kind of compare, when we want to do one versus the another, and that may be a good time to kind of re-ask that question. Right. So this is. So we want to model P of x given y, and at prediction time, when we want to make a prediction on a new example x test that is given to us, so P of y given x, where x is like a new example, we can use the Bayes rule to swap it around. This will be P of x given y times P of y over P of x, right? P of x given y and P of y is the direct chain rule expansion of the joint, and we get a P of x in the denominator. And this can also generally, in cases when y is binary, we can write this as P of x given y times P of y over P of x given y equals 0 times P of y equals 0 plus P of x given y equals 1 times P of y equals 1. Right? And we can write it this way because P of x is exactly equal to this when y is binary. Right? So this is the Bayes rule to get P of y given x, and P of y given x is generally called the posterior distribution. And when we want to make a prediction as a class rather than a probability, right? So P of y given x will give you the probability of, say, y equals 1 given x or y equals 0 given x. But when we want to make a prediction of whether example x belongs to the class y equals 0 or y equals 1, we generally do it this way. So y hat equals argmax of y, P of y given x. Right? Which is the y that has the highest posterior probability? Does y equals 0 have a higher probability, or does y equals 1 have a higher posterior probability? Right? And this is the common recipe for making predictions, whether we are using Gaussian discriminant analysis or naive Bayes or any generative model in general. And in order to do this prediction, you may observe that P of y given x, we can write it like this, P of this is the argmax over y, and P of y given x was P of x given y, P of y over P of x. Okay. In order to calculate the argmax over y, we observe that P of x, the denominator, is just some constant, and it's going to evaluate to the same value for the cases of y equals 0 and for the case of y equals 1, which means this is the same as argmax over y, P of x given y times P of y. Right? So for the purposes of making a prediction of which class we want to assign an example to, we don't even have to calculate the denominator. Yes, question?
Of the y class divided by total example in the condition. But what does P of x mean? So that's the probability of occurrence of a given.
Yeah. So the question is, P of y has a meaningful interpretation. You can think of it as a fraction of examples that are positive. What does P of x mean, right? And P of x means, it can mean different things in different problems. So P of x, you can think of it as what's the probability that you're going to encounter this example, this input in your population. Right? That's one way to think of it. And it could have, it could belong to class 0 or class 1, but you're, given an input example, you're trying to answer the question, what's the probability of encountering that input? Right? That's a rough intuition. Yes, question. What's the significance of maximizing y? So what we are calculating here is we are trying to find out which value of y results in the highest posterior probability, because we want to consider that value of y as our prediction. Does that make sense? Yeah. So if our goal is to just make a decision of choosing y equals 0 or y equals 1, then for that problem of making a decision of y equals 0 or y equals 1, we don't even have to calculate the denominator. But if we want to calculate the probability of y given x, then we absolutely need to calculate the denominator. Right? The two are different problems. Right? If you want to calculate the exact probability, is it 0.77 or 0.5 or 0.2, then you absolutely need to calculate the denominator. But if your problem is to only decide whether probability of y equals 0 given x is greater than or lesser than probability of y equals 1 given x, just to do the greater than or lesser than, then you don't need the denominator. Yes, question? So in this case, the question is, won't the probability of x change depend on what class it came from? So in this case, we have marginalized out the class. Right? So you're just considering all the examples in one common pool where they're mixed with all the classes, and just going to pick one example at random and ask what's the probability that you observe the input. Right? So in this setting, we're going to cover two different algorithms. Right? Two algorithms for today. And for both the algorithms, y will be discrete. Right? So the first algorithm is GDA, Gaussian discriminant analysis. In this, x is continuous. Right? And the other algorithm you're going to consider is naive Bayes. In this, x is discrete. Okay? And the example that we're going to use is text classification. Right? So in discriminative algorithms, when we had two different kinds of algorithms depending on whether y was continuous or discrete. Over here, our focus is on x, and we're going to get two different kinds of algorithms depending on whether x was continuous or x was discrete. But we are limiting ourselves to the case of classification only. So we're going to limit ourselves to y equals 0 or 1, but your x's can be continuous or discrete. Right? And before we jump into our first learning algorithm, jumping into GDA, just some terminology. So the model, we call the joint probability of P of x comma y as the model. So this is the joint P of x comma y. And it is common practice to define our model or express our model as a data generating process. Data generating process, and this process is represented as a hierarchy of steps with which we generate our model, and this has a one-to-one correspondence with the way we factorize our joint probability. Right? Now, what does this mean? Let's see the case of GDA to get a concrete sense of what we mean by this. So GDA, this is our first generative model. So in GDA, we define the model like this as a data generating process. So Y is sampled from a Bernoulli with parameter phi, and X given Y is sampled, X equals Y equals 0 is sampled from a normal distribution with mean mu naught and covariance sigma. X given Y equals 1 is sampled from a normal distribution with mean mu 1 and covariance sigma. Right? So this is a hierarchy of steps with which we can generate our data. So first sample a class variable from a Bernoulli distribution with parameter phi that decides whether the example that we are about to generate belongs to the class y equals 0 or does it belong to the class y equals 1. And then we generate the input x given y equals 0 according to a normal distribution with some mean and covariance, and if y equals 1 we generate the example as a sample from a different normal distribution with mean mu 1. But in this case, we are sharing the covariance matrix, and we'll go into the details of why we do that later. But for now, assume both the normal distributions share the covariance matrix, but have different means. Right? And for this sequence of steps, the corresponding distributions will be P of y equals phi y times 1 minus phi to the 1 minus y. And this is the Bernoulli distribution, and P of x given y equals 0 is equal to 1 over 2 pi to the d by 2 1 half minus half x minus mu naught transpose naught. Similarly, P of x given equals 1 and here y is in 0, 1 and x is in RD. Right? So what do we have here? So P of y is a simple Bernoulli, and let me just write the parameters in a different color. So these are all parameters. P, and P of x given y equals 0 is parameter here. Mu naught, sigma inverse mu naught, and similarly in this case we have right. So y is discrete, it's either 0 or 1, and depending on what y we sampled, we generate an x, that's the input, based on either one of the two Gaussian distributions with different means, but they share the same covariance structure. Right? So, the generative algorithms, one way to think of them is in discriminative algorithms, you are asked to differentiate, or given an input example, you are asked to decide whether that example belonged to one class or another class, right? Where you're kind of acting like a critic, where you're given an X and you're asked to classify it as X versus Y. Whereas in generative algorithms, the way you think of them is you're asked to kind of generate the input. You're kind of you're kind of acting like an artist. You're trying to construct an example X, which look different for different examples, right? And for different classes. So the goal here are kind of different in some way, where in one case, in discriminative algorithms, all you're asked to do is have good power to discriminate whether an example belongs to y equals 0 or y equals 1, which means you may limit yourself to just look for certain cues in the input that help you discriminate it and just ignore the rest of the example. Whereas in generative algorithms, you're asked to generate an entire example, right? You're expected to come up with a full description of what makes up a good algorithm of a good image or a good example of y equals 0 or y equals 1 class, right? So in general, generative modeling is a harder problem compared to discriminative modeling, and you can also see that because p of x comma y is equal to p of y given x times p of x, which means in order to learn a generative model, you have to learn a discriminative model and also learn something else, right? So generative modeling in general is a harder problem compared to just the problem of learning one of the conditionals, right? So this is, think of this as discriminative, and this is generative, and you have something extra as well, compared to discriminative model. Yes, question?
So if someone gives us some data below here, like all the parameters, mu naught, sigmas, and we will try to generate more examples in different categories, but we won't make any predictions here.
So the question is, with a generative model, given some training set, for example, we learn how to generate new training examples, but we won't make a prediction. Is that the question? Yeah. So the question, the answer to that is no, because we are studying these in the context of supervised learning, which means our end goal, at least in this part of the course, is still making predictions, right? And what we are doing is that we are learning the joint distribution, which means not only can we generate new examples, we can also discriminate them, right? Exactly. So when we want to discriminate, we will use the Bayes rule to construct a posterior distribution, and the posterior distribution, and here's a recipe to construct the posterior distribution using the generative modeling components. And we can use this recipe to make predictions on new examples. All right. So back to GDA. We have defined the model like this, where y is binary, it's 0 or 1, x is continuous, and the parameters of this model. The parameters are phi that belong to the Bernoulli, mu naught that belong to this distribution, mu 1 that belongs to the third distribution, and sigma that's common to both. Right? So first we define the data generating process. In order to come up with this step, you don't need any data. Right? This is just math. You're making an assumption that this is the way your data is generated, right? And with this assumption, we have already defined our probability densities. We have determined what our parameters are, and then we observe data. And when we observe data, we can use the data to fit our model and learn these parameters using maximum likelihood. So maximum likelihood to learn parameters. In order to perform maximum likelihood, the first step is to write out the likelihood function or the log likelihood function. And in this case, the log likelihood looks like this. So it is, the likelihood is a function over the parameters, not the data, right? A probability density is a function of the data and assumes parameters, and the likelihood is a function of the parameters phi mu naught mu1 sigma, right? And this is I equals 1 to n, the joint p of xi comma yi, right? And this is where generative modeling differs from discriminative modeling, right? In discriminative models, we use p of y given x, and in case of generative models, we use the joint p of x comma y. And this is the key difference between generative models and discriminative models. In generative models, we are interested in the joint probability of p of x comma y, and in discriminative models, we only care about p of y given x. This question.
Can you explain qualitatively what is that? So p of x comma y is just saying that what is the likelihood that I have this data in the training?
Yeah. So the question is what's the intuition about this? And yeah. So the intuition is exactly that. What's the probability, or well, probability is the wrong word in this case. It's the likelihood. But if you just focus on this, then it's the probability of finding a specific XY pair if you just sample it from your population of examples.
And as opposed to what is p of y given x in the discriminative, like in words, what is it saying?
So in the analogy in case of p of y given x is you're given an x, right? You had no x was not sampled. Somebody gave it to you, right? And now for that given x, what values of y could it possibly have? Right? We kind of limit ourselves to a universe where we have only one example, right? P of y given x, and given that x, most of the times it could be say y equals 1, but sometimes it can be y equals 0, and that's your probability of y given x.
But why does the product, so here the product makes sense, but why does the product make sense in a discriminative? So the product is to say over all the tuples, all the x comma y tuples in the training set, you take the product. So you want the likelihood that you have all those in the training set. But why does the product make sense in a discriminative?
So the question in the discriminative sense, why did this product make sense?
Yeah.
So in the discriminative case, we had product I equals 1 to n p of yi given xi. In this case, for each example, we are assuming x got decided somehow beyond our scope. Somebody else decided x for us for this example, right? And there are n such situations where x got decided to different values in each situation, and we are only interested in modeling y for those specific examples, right? And so here we get one probability, here we get a different probability, another probability, and the joint is just the product of them because of the independence assumption. And similarly here, in this case, the joint is just the product of the individuals because of the IID assumption. And this we can write it as log of I equals 1 to n. Now just break it down. P of xi given yi times p of yi. And we know what p of xi given yi and p of yi are, and they are right here. So we plug them in here, right? Take these definitions of x given y and p of y, plug them in here, right? And solve take the log likelihood and maximize it with respect to the parameters, right? And you get estimates for theta hat, phi hat, mu hat, sigma hat. Once you solve for the gradient of this with respect to your parameters equal to 0, solve for them, and those are your estimates. Right? We've done this for linear regression, and you can follow something very similar here. This question?
What in this example are we interested into maximizing the product of observability and its conditional one, because technically we can know it, and of course the formula here and the hypothesis to calculate it. So is it fine because it's easier to calculate at C level, or is there some theoretical reasons?
So the question is, in this case, why don't we just maximize the conditional of y given x, right? And in order to define what is y given x in this case, going by this data generative process, y given x does not have a straight answer, right? So the data generating process only tells us what is x given y, and that's a normal, right? So what's y given x here? We have to apply Bayes rule. Right? And in order to apply Bayes rule, you need to be able to compute the individual parts of the Bayes rule. And in order to compute them, you need to solve for the parameter values. And the way we solve for the parameter values is by doing maximum likelihood. Right? So maximize the joint likelihood. You get the parameter values which fit the data, and then you apply Bayes rule to get your conditional P of y given x. Yes, question?
Is there a closed form solution? Is there always a closed form solution when you differentiate it, or do you have to?
Yeah, so coming to that next. Was there another question? Yes.
So shouldn't you technically be dividing by P of x, but it doesn't matter in this case? Because you're saying you are using Bayes rule, so you should be dividing it by probability of x.
So the question is, should I be dividing by P of x over here?
Which won't matter at the end, but...
So the question is, do we need a P of x here over here? And we need the P of x over here only to get P of y given x, right? But in generative models, we are, for P of x comma y, you don't need a P of x in the denominator, right? In generative modeling, this is our likelihood objective, right? And that's the fundamental difference between discriminative models and generative models, right? In discriminative models, this will be P of y given x, in which case you technically need a P of x here. But for generative models, we want to have the ability to generate a new full data set by just sampling from the model. So moving on. So take the derivative, set it equal to 0, solve for the different parameters, and what we get is phi hat equals 1 over n, I equals 1 to n, equal to 1. And these are the closed form solutions for if you take this objective, plug in the densities, treat it as a likelihood, differentiate, take the partials with respect to each parameter of this entire expression, set the partials equal to 0 and solve for the parameters. These are the solutions you get. And this is what is there in your homework. Right? Yes, of course. So, so the question is, okay, so let's go deeper into what each of these terms mean. Over here, we are using this notation, right? So this is, supposing there's some expression here, this is basically equal to 1 if expression is true, and 0, if it's false, right? So each of these, so yi is 1 for a few examples, 0 for a few other examples. So here we are basically counting the number of examples for which yi equals 1 and dividing it by n. So what fraction of your examples are labeled 1 is what phi hat will evaluate to. Over here, for mu naught, we are summing over those xi's for which yi equals 0, right? Because this indicator function, so this notation is called an indicator variable. So this indicator function will evaluate to this indicator function will evaluate to 1 only for those examples for which yi equals 0. So you're only summing over xi's for which yi equals 0, and here you're counting the number of examples for which yi equals 0, right? And similarly here you have you're doing the same for mu1. Now what's the deal with sigma here? There are no indicator variables here, but what we observe here is that for each examples we are subtracting it from the mean that is specific to that example. So we have two means, one mean for yi equals 0 and another mean for yi equals 1. What this means is subtract from x the mean which belongs to its yi. Does the notation make sense? Subtract from x the mean that corresponds to its label. Right? And this is basically, these are the solutions, and in your homework you will be deriving it and proving that these are actually the solutions, which is basically just calculus. It's the computation can be a little verbose, but it's pretty straightforward. And yeah, so these are the MLE, the maximum likelihood estimates of the Gaussian discriminant analysis. So we start with defining a model, get the corresponding densities or the probability distributions, identify what our parameters are, right? Write out the log likelihood objective as the product of the joints, because that's what we model in generative models. We model the joint distribution and break it down into components. And the way we broke this down as p of x given times x given y times p of y was because that is the factorization that we readily have at our hand. Plug in the appropriate densities for p of x given y and p of y in this likelihood objective, and take the derivative of the entire likelihood objective with respect to the parameters, set them equal to 0, solve for them, and you get these. Yes, question? Yes, this should be sigma hat. Thank you. Yes, question?
Let's say if we don't like indicator functions, can we just write that as summation over class 0?
Yeah, so if we don't like indicator functions, you could, for example, write this as this is just equivalent notation I such that yi equals 1 of xi over summation over I such that yi equals 1 times 1. Right? So this is just another notation which calculates or results in the same value. Right? Here we are explicitly multiplying some of the x's by 0, and here we are just skipping over them in the index. Both are equal notations. Yes, question?
For different bias, do you have to have the same probabilistic model when you have normal for one Poisson?
So the question is, can we have normal for one class, Poisson for another? You technically can. You can define your model any way you want. The question is that meaningful? Right? A Poisson is basically counts. So and a normal is real valued. So if you already know that some of your data are counts belong to one class and the data that take real values belong to another class, then you kind of already why go through this exercise in a way. But from a statistical point of view, you can absolutely do that. Except those x's that have Poisson must be count valued or integers, positive integers, and those x belong to the normal must be real valued. So if you have a way to kind of make your math compatible with some x's having a different data type versus other x's, then yes, you can absolutely do that. Yes, question.
So we have the assumption that the quadratic function is a concave function, or we just take it as a trial knowledge.
So the question is, in this case, will this be a concave function? In this particular case, I believe it is, but in general, it need not be. Right? In general, it need not be, but I think in this particular case, it is.
So how can you just get the gradient and take it as 0 and get the maximum value?
Yeah. So in cases when so the question is, is this concave, and how can we do this without knowing? In this case, it is concave, and so this works. In general, just taking the derivative and setting it equal to 0 may not work, but in those cases where so if you it so happens that for cases where closed form solutions exist, they tend to be concave. And for cases where you don't have closed form solutions, you tend to do gradient descent. So you can optimize this using gradient descent. And in that case, if you're doing gradient descent, you will reach some kind of a local maximum. Yes, question.
Intuitively, can you explain what it means for y equals 0 and y equals 1 to be the same signal?
Yes, we're coming to that next. Right, so let's move on. So here we see that by following the above steps, we calculate the parameter values for the joint, and using the recipe given here, you can construct a posterior distribution for y given x using plug in p of x given y, which is Gaussian, p of y Bernoulli, Gaussian, Bernoulli, Gaussian, Bernoulli, and you will get an expression for p of y given x. And it so happens that for the case of Gaussian discriminant analysis, with the shared sigma variable, shared covariance, we see that the posterior distribution takes the form of the logistic regression. What do I mean by that? Let me write it out to make it more concrete. Right? So if you go through this exercise of calculating the posterior distribution for Gaussian discriminant analysis, we get p of y equals 1 given x can be written in the form 1 over 1 plus exp of minus theta transpose x, where theta depends only on mu naught, mu 1, phi and sigma. And this is also on your homework, where you need to where you show that given a Gaussian discriminant analysis model, you can represent the posterior distribution of y given x can be represented in this form, where theta can be represented only with mu naught, mu 1, sigma and phi. Right? So this means the intuition to have here is let's assume we have mu naught here. So here this is x1 xd. So let's say this is mu 0, mu 1. Use a different color for this. Mu 1, and they share. So we have two different means. Each mean is specific to each class, a blue class and a red class, and both of them share the same covariance structure. Right. So if we write out the contour lines for some for these examples, they might look like this. So these are the contour plots for the density of class 1, and these are the contour plots for the density of the other class, and our examples are sampled from these Gaussians. So let's say we have for the red class, we have some examples. Right. So we start with just the data points, and we fit a GDA model, and your GDA model would learn these to be your mu's or values sufficiently close to be the two mu's and the two sigmas, and the common shared covariance structure, and phi would just be the fraction of examples in the red and fraction of to the total fraction, for example, and the posterior distribution, which you can think of as the separating hyperplane, which corresponds to p of y equals 1 given x equals 0.5, which is also equal to p of y equals 0 given x. So the set of all points, x points, for which the y equals 1 class and y equals 0 class assign, where the point has equal probability of belonging to the y equals 1 class or the y equals 0 class, would be something like this. Right? And the claim here is that for any Gaussian discriminant analysis model that share the same sigma, the posterior distribution of y given x can be represented as a logistic regression model, where the thetas only depend on the parameters of the model. So which means GDA, any GDA can be written as a logistic regression model. Now, the reason why the two covariance structures or the two the two covariance structures are similarly oriented and similar in shape and size is because they come off the same covariance matrix, and these ellipsoids are the shape and orientation and size are completely determined by the covariance matrix, and the principal axes of these covariance matrix are basically the eigenvectors of this covariance matrix, and the eigenvalues tell you how spread they are in each of those axes. Yes, question?
So is the hyperplane dependent on phi? Does phi decide the hyperplane?
Yes, the phi also decides where the hyperplane will reside. Yes, the hyperplane will depend on phi. It's going to depend on phi, mu naught, mu 1, and sigma, all the variables. Exactly. So this theta over here is vector valued. And the value of theta naught, theta 1, theta 2 will be a function of these parameters. This question.
What we drawn there are the contour blocks, right?
Yeah.
So P of y equals 1 given x will, let's say, have some constant value k, will be a ellipsoid around mu 0. And similarly for mu 1 also. Then y will just have been equal to.
Oh, actually, you're right. So this should not be. Yeah, it shouldn't be. It should just be equal. It shouldn't be 0.5. You're right. Thank you.
But why should it be a line? Just because they have this.
So it's a line because you can represent it in this form, and this is your logistic regression, and Yes, there's a question. So the question is, what if they have different covariance matrices? We made an assumption that you're going to assume that both the classes are going to share the same covariance matrix, right? And if the two classes don't have the same covariance matrix, you can think of it like this, right? So one class will, let's say, is concentrated over here, and wait a second, what did I write here? So this I completely messed it up. Sorry. So the line that corresponds to P of x given y equals 0 equals P of x given y equals 1. Sorry. Right? Does that make sense? The set of all points which have the same density under class 1 and the same density under class 0. Right? That would be a straight line in this case. In case of if we have two different covariances, your examples may look like this. Right? So you have some examples that are, say, more concentrated here. Another class examples are more dispersed. Right? And in this case, the set of all points that have the same probability under class 0 and class 1 would actually look something like instead of a straight line. So these would be the set of all points which have the same probability under class 0 or under class 1. If both of them share the same covariance structure, then this line will be a straight line. And if they have unequal covariances, then it can actually be represented as a quadratic instead of a linear. Yes, you can think of it as logistic regression with polynomial features. Yeah, that's one way to think of it. Yes.
Since the hand one has a larger covariance ellipse, shouldn't the discrete boundary
I would encourage you to plot it, and you'll see that it's going to curve towards the one which is more concentrated. Just take two covariance structures and plot the set of points which have equal probability under both classes, and it's going to come like this. Any other questions? Okay. So a GDA model for a given GDA model will uniquely determine a logistic regression model for its posterior distribution, whereas the converse is not true. If you have a logistic regression model, it may not be the posterior distribution of a GDA model, right? It need not be a posterior distribution of any model, or it could be a posterior distribution of some other model. Whereas if you have a GDA model, its posterior is always a logistic regression model, right? And the GDA model is making a stronger assumption, in the sense that it is making a stronger assumption that your data is actually distributed according to Gaussian distributions. The two classes actually have a Gaussian distributions with the shared covariance structure. It's making that assumption. Now, if that assumption is true, then your GDA model will tend to be more efficient, or more asymptotically efficient, or more sample efficient compared to logistic regression. Right? When the assumption holds true, then GDA is a better model. You probably need a lot fewer examples to get some level of accuracy compared to a logistic regression. However, logistic regression does not make any assumption and tends to be more robust. It might need a little more data in cases where the assumptions are true, but it tends to work well even when the assumptions are not met. It's a pretty robust algorithm. And in practice, almost always logistic regression should probably be your first choice of algorithm to try out on a given data set, because assumptions may or may not hold true. In cases where the assumptions do hold true, GDA will be slightly more efficient in terms of the number of examples required. Right, that's and in your homework you will also basically see you'll be seeing this phenomenon in your homework as well, when you plot your data, some of which may be distributed according to Gaussian, some of which are not, and see your the model performance between GDA and logistic regression on both those situations. All that is part of your homework question 1. Any questions before we move on to naive Bayes? Yes. So under what assumptions can you map logistic regression back to GDA? The extra assumption is that your x's are coming from a Gaussian and having same covariance. All right, let's move on to naive Bayes. The center line, okay. Yes, so if the covariances are the same, then the line that has equal probability under the two classes will be a straight line. Yes. So when you solve for 1 over 1 plus e to the minus theta transpose x equal to 0.5, you will see that theta transpose x must be equal to 0. So that will be a line. All right, naive Bayes. So in GDA, we saw that the x's are real valued. They live in some d-dimensional real space. But that's generally not how, that does not account for all the different ways in which we encounter data. For example, our data may be text messages, emails, and we may want to build a spam classifier for whether a given text message or email is spam or not. In those cases, your inputs are basically strings. It's a list of words, and that doesn't fit well as a multivariate Gaussian. And so when x's are discrete valued, that's when we use naive Bayes. In order to use naive Bayes, x is discrete valued. Most commonly we use it for text classification. Right? For example, spam filters. That's going to be the running example today. And this would be a good time to review conditional independence, a concept in probability. Right? So conditional independence means given two random variables xj and xk, we say they are independent if probability of xj given xk equals probability of xj. Right? This is the definition of independence. We say they are, so this is independence. We say they are conditionally independent when conditioned on some new random variable, say y, let's say y. So p of xj given xk comma y equals p of xj y. This is conditional independence when conditioned on y. Right? Now, can anybody tell me, does independence imply conditional independence? Does conditional independence imply independence?
No.
And what is the answer to the first one? Does independence imply conditional independence? So does independence imply conditional independence, and does conditional independence imply independence? Yeah, that's correct. So both, the answer is no to both. Right? In general, conditional independence, your random variables could be conditionally independent. That doesn't say anything of whether they are independent or not. They may not be conditionally independent, and even that does not say anything about whether they are independent or not. Right? Conditional independence assumes assumes that both sides are conditioned on a third variable like y. And in this case, we are going to make use of conditional independence. And this is just a refresher for what conditional independence is. Yes, question? Right. So the first, in naive Bayes, we are going to consider two different kind of event models. The first model that we are going to consider is called the Bernoulli event model. So in the Bernoulli event model, the mental picture to have is, let's say we have a text message which says, buy our lottery. Right? So this is a sequence of alphabets, right? And we want to convert this into some kind of, a vector. And the way we do that is to come up with what's called a multi-hot representation, where imagine you have a long vector where each component of the vector is associated with some word in the dictionary, right? So let's say the first component belongs to the word A, and if you go through some dictionary, here we're going to assume English, but the concepts apply for anything. So second word in the dictionary would be, say, aardvark. And the third was aardwolf, and so on. And then the word buy is going to show up in your dictionary. Lottery, hour, and some last words, Z, Y, G, M, or G, Y. All right, some word, right? And first we're going to convert our sequence of words into a fixed length vector. where you have zeros in places for those words that do not appear in the message, right? And 1 in places where those words do appear in the message. Right? So we're going to assume a fixed set of words which is called the vocabulary, right? And we assume this vocabulary for each word to have a fixed location in this long vector, right? And given a new input text message, we will convert it into a fixed length vector where we have zeros in places where the word does not appear in the text message, and 1 in places where the word appears in the text message. It doesn't matter how many times it appears. The question is, does it appear once or more? Yes, question?
Out of curiosity, is this actually how Stanford does it?
We're going to talk about it, right? So here, X is, so if our vocabulary has D dimensions, right? So if this count is D, then X belongs to 0, 1 to the power D. This is how we write a D-dimensional vector where each element is either 0 or 1, right? And any given xj is either 0 or 1, right? And we make the assumption that P of xj, and we write out our model like this, right? So this is our model now. Just as the way in case of the Gaussian discriminant analysis, we had a hierarchical model that described how the data was generated. Similarly, we're going to have a model here. P of y equals 1 equals phi y, and P of xj given y equals 0 equals phi of j given y equals 0. So we're going to assume that there is one Bernoulli distribution parameterized by phi y, where phi subscript y is one value between 0 and 1, and that's the parameter of this Bernoulli distribution, which tells us what fraction of our overall text messages are spammy versus not, right? It's just the class prior. And then we have two sets or two collections of Bernoulli variables. One set for the class y equals 0. So for y equals 0, we have a phi j for each j from 1 to d, which tells us what's the probability that xj equals 1 when the class is 0. And another set of Bernoulli variables, a full set of Bernoulli variables corresponding to y equals 1, which tells us what's the probability that xj equals 1 when the class is 1. So what this means is, what's the probability that this word, the word corresponding to the index j, will show up in an email that is spammy, and this tells you what's the probability that a word indexed by j shows up in an email or text message that is not spammy. This question. So what's the number of parameters here? So here we have one parameter. here we have, technically we have d minus 1 parameters. No, so here we have d parameters, and here also we have d parameters. So 2d plus 1 parameters. Good question. Does it make sense? We have one parameter to give us the class priors, whether just, what in the entire population, what fraction of messages are spammy versus not, and then condition on, by limiting ourselves to say only the spammy emails, then we have one parameter for each word that tells us the probability that the word will appear in a spammy email, or the probability that it will appear in a non-spammy. Yes? So there are d such distributions for each j. So j can be from 1 to d. So you have d such Bernoulli distributions.
So for any given j, is there not any straightforward way to go from p j given y equals 0 to p j given y equals 1?
I'm sorry, I didn't get the question.
There's no way to relate them given a j, like those two.
Now there are two different sets of variables, right? Two different sets of distributions. Right? And for this, so this is our model, and we can write out the likelihood function for phi of y, phi of j given y equals 0, phi of j given y equals 1. So basically think of this as, this is one parameter, this is a set of d parameters, this is another set of d parameters, and the likelihood can now be written as the probability of, or the log probability I equals 1 to n, p of xi, yi, given the full set E, and this can now be written as I equals 1 to n, p of y I given p of y I, phi of y times product j equals 1 to d p of x j I given y I phi. Right? And the way we came up with this term as the product of all the different xj's is using the conditional independence assumption. What that basically, the way we came up with that is p of, say, x1, x2, xd given y. This is p of x given y, can be written using the chain rule as p of x1 given y times p of x2 given x1 comma y times p of x3 given x1 comma x2 comma y, and so on. And with the conditional independence assumption, each of this becomes p of x1 given y, and with the conditional independence assumption, this becomes p of x2 given y, and this becomes p of x3 given y, and so on. And this product is what's written here. Right? So, just the way the IID assumption allows us to factor out different the probability or the likelihood of or the probability of the full data into product of the individual probabilities. Similarly, conditional independence allows us to break down this full collection given y as the product of the individuals. Right? So this is the likelihood, and each of these we know is a Bernoulli, and we know the probability density of a Bernoulli. Plug them in, take the gradient, take the partials with respect to each parameter, set it equal to 0, and by doing that we get the maximum likelihood estimates. So that MLE estimates phi j given y equals 1 is equal to I equals 1 to n x j 1 right. What does this mean? The probability that the word belonging to the jth index in the dictionary is the probability that the jth word in the vocabulary is going to show up in a spammy email is equal to the number of times the word appears in spammy emails divided by the total number of spam emails. Right? This expression looks a little cryptic, but it's actually pretty simple. What it's doing is you scan over every email or every text message I equals 1 to n and count the number of times or count the number of text messages where the jth word appears and the message is spammy, and divided by the total number of emails, total number of text messages that are spammy. It's just calculating in what fraction of the spammy emails does the jth word appear. Right? The syntax looks a little cryptic, but it's the idea is very simple. Yes, question? This phi. So this phi is basically the full collection. I've just written it as phi. It's 2d plus 1. Yes, question? So and similarly, phi j given y equals 0 is equal to same story, I equals 1 to n, indicator x I j equals 1, and so this is the logical and, right? And y I equals 0 divided by equals 1 to n, indicator y I equals 0, right? And finally, phi y is equal to I equals 1 to n, indicator yi equals 1 divided by n, right? So the phi y parameter is estimated as the number of spammy messages divided by n, right? And for each class of spammy versus not spammy, you get a full collection of Bernoullis per word, and they are estimated as the number of messages in which the word appears divided by the total number of messages in that class, and it's the same definition here, but we just switch y equals 1 here. Yes, question? This one? So here we just broke down the joint into the factors, right? So think of, we start with this joint, and you can write this as p of xi given yi times p of yi, right? And this one we factorize it using the conditional independence assumption. Right? So this is just the factorization of this by making use of the conditional assumption, conditional independence assumption. Yeah, this parameterized by phi of y. Yeah. Yes, question?
Just to check. So there's a conditional independence meaning if a word appears together most of the time. I mean, does it hold it?
So what does conditional assumption mean here? It means when you know when a message is spammy, then the probability of word A appearing is independent of whether word B appeared or not in it.
But if a
Yes, so if certain words always appear together, it does violate the conditional independence assumption, but we are just going to make that assumption anyways, just to make the math simple. Yes.
So intuitively, like it ignores the order that the ones.
Yes, this ignores the order in which the words come. Yes.
Yeah, but given a spam mail, not necessarily the words in the email are like spamming, right? Like the words also normal.
Yes. So in a spammy email, some words are not necessarily spammy, right? Like words like the and are not necessarily spammy. But what we see is that by making this assumption and by this set of assumptions generally tends to work well in practice, even though there are the intuition there is that if a word has no significance in terms of its indicative power, then it's going to contribute equally to both the classes and its effect kind of cancels out. That's the intuition to have. Like common words will have equal weight in those for both classes, but words that have a high indicative power of spamminess will bump up the class probability higher. Right? So that's the maximum likelihood estimate. And from this, how do we make predictions now? So we follow MLE and we estimate all the parameters. And once we have estimate the parameters, we're going to make predictions using the Bayes rule. So the Bayes rule tells us P of y equals 1 given x is equal to P of x given y, P of y given x times P of y divided by P of x, and this is equal to P of x given y times P of y over P of x given y equals 0 times P y equals 0 plus now to make predictions on a new email x, we're going to first convert it into a feature vector of d dimensions, and we're going to calculate these terms. So P of y, we estimated and here we're just going to use phi y, and this is basically the product I equals 1 j equals 1 to d x j I given y times P of y divided by the denominator, right? And using again using the conditional independence assumption, we can break down the long vector of the feature vector of the new email into product of the individual Bernoullis, right? And multiplied by the class probability, we get the probability of P of y equals 1. So we do P of y equals 1 given x equals, and similarly you can calculate P of y equals 0 given x to be the same thing with but and in order to make a prediction, what's commonly done is you calculate numerator 1 and you calculate numerator 2 and see which of the two numerators is bigger than the other. All right. So one problem that we may encounter with this method. So any questions on this so far? Yes, question? So these two add up to 1. Once you calculate the denominator and normalize them, they will add up to 1, but just the two numerators need not add up to 1. Yeah, if you want to get the probability value, then you need to calculate the denominator. But if all what you want is to make a decision of which of the two has a higher probability, then you don't need to calculate the denominator. Right? So one problem that we may encounter with this method is what happens if at test time we encounter a word that was never seen in the training set, right? So our in this model, what if the word, say, aardvark, never showed up in our training set, neither in positive examples nor in negative examples, and we end up estimating the fees for the word aardvark to be 0 and 0 because the numerator is 0 in both the places. And at test time, what do we do? At test time, it means for the word aardvark, at test time, we're going to end up with 0 over 0 plus 0 because this is going to be 0. If the word aardvark appears in the email, the probability corresponding to the word aardvark will make the entire thing equal to 0. And similarly, this will also factorize, and the word aardvark will make this 0, and you're going to get a 0 over 0 when you encounter words that you have not seen before. So basically, with this method, a problem is if we encounter a message at test time that has a word that never appeared in the training set, either as class 1 or as class 2. The method does not tell us what our prediction should be, right? And for that, what is commonly done is a technique called Laplace smoothing. So Laplace smoothing was invented by Laplace, and the origins of Laplace smoothing goes something like this. So Laplace was basically trying to calculate the probability. What's the probability that the sun is going to rise tomorrow? What's the probability that the sun is going to rise the next day, right? And in your training set, you basically have only positive examples, right? So every day, if you look at the past 100 days or 1,000 days, you start collecting your data, right? Every day the sun is rising, right? And in your your training set has only positive examples. And now, when you estimate the probability of the sun rising the next day, your MLE estimates will give you a probability equal to 1, right? It will always be exactly equal to 1. And his claim was that that is suboptimal, right? The probability that the sun will rise the next day at some day in the future is going to be 0. Might be, the sun may not rise, someday, and so he invented with the correction that he came up with is commonly called as Laplace smoothing. And the idea of Laplace smoothing is, supposing you have, let's say you're doing coin tosses, right? So let's say you're trying to estimate the bias of a coin. Let's call it phi, and your x's are 0 and 1. Now you take a coin, flip it 10 times, and let's say the coin turns up heads for all the 10 trials. What is our estimate of phi in that case? If phi is supposed to be probability of heads, right? So the MLE estimate tells us that this is going to be 10 over 10, and so our parameter would be the phi would be 1. But what Laplace smoothing tells you is the way to kind of think about that is, let's say you're keeping 2 counts, so count of heads and count of tails, right? In pure maximum likelihood, we start with the 2 counts being 0, and as we keep conducting trials, we add a 1, and so on, and then we sum up the count h over sum over count h plus sum over count tail, right? What Laplace smoothing tells us is before we even start conducting our experiments, start with a count of 1 for all your classes. Right? Assume a uniform probability before we start conducting our experiment, and then start your trials and observing data and incrementing the counts. Right? And with this technique, we see that because we start with a count of 1 on both sides, even if all our 10 experiments come up with a +1, the probability of heads in this method will be 10 over 11. Right? It will never be exactly 1. And similarly, the probability of tails will keep going down as we collect more data. It's going to start with 0.5, and as we keep running experiments and the probability we keep getting only heads, this keeps coming down, right? But it will never be exactly 0. Right? This is the idea of Laplace smoothing, and this Laplace smoothing can be applied to our spam classifier as well. Right? So assume that we have seen every word once in a spammy email and once in a non-spammy email. Right? Initialize your counts to that, and then start observing your data and accounting for your data. So the Laplace smooth version of so the Laplace smooth version of our estimates will be like this. So for comparison, here is the maximum likelihood estimate, and the Laplace smooth estimate would be phi j given y equals 1 equals 1 plus sum over I equals 1 to n xj I equals 1 and yi equals 1 divided by 2 plus sum over to n right. So the idea here is you add 1 to your to the count, and you add the number of classes in your problem to the denominator. So you add 1 to the numerator to say you've seen that word at least once, and you divide it by 2 to account for the fact that that this evaluates to a probability, a valid probability density, a valid probability distribution. Right? And similarly, the Laplace smooth version of j given y equals 0 will be 1 plus so this component in the denominator comes from the data, the number of messages which are spammy, and then you assume you've seen 2 more messages, one message in which the word appeared and one message in which the word did not appear. Right? And over here, since this is the probability that the word appears, you assume you've seen the word appear in one message and also in the rest of the messages where the word actually appeared. Right? That's the idea of Laplace smoothing. Right? And this is, if you're familiar with Bayesian statistics, this is like imposing a beta prior on your parameters. If you don't know what that is, don't bother. But it's not only is it just a heuristic argument, there's also a principled explanation of why this is a good thing to do. All right? So that's Laplace smoothing. And now we and this model is what's also called as the Bernoulli event model. And there's another variant of naive Bayes, which is called the multinomial event model. Right? So in the multinomial event model, which is a slight variation of this, which means a lot of the terminology is going to show up here, but may mean slightly different things. So please pay attention. It is a slightly different model, which makes a different set of assumptions. And the assumption it makes is that, y again comes from a Bernoulli, the parameter phi. But then each word in your email, which is either spammy or not spammy. So x given y equals 0 is sampled from a multinomial. Well, so the correct is actually categorical, comes from a categorical distribution. And we're going to still call it phi, except now phi is a d-dimensional categorical parameter vector. In fact, here it will be, so this is one-dimensional phi of y, and phi of k given y equals 0 will be d, let's not call it d, will be the size of your vocabulary minus one dimension. What does this mean now? So first I'm going to write out the expressions and then give you some intuitions about this. Right. So the Mle estimates here look like this: phi k given y equals 1. Here the assumption is that here xj indicates the word in the jth position of your text message, and that is a word that exists in your dictionary. So v is the vocabulary, and this means the size of your vocabulary. So xj, or the jth word in a message, takes a value between 1 and the size of your vocabulary. And xi, which is the ith message, is the full message of your ith example, has length di. So each message can have a different length, right? And xi is now a vector of length di, where each component can take one of the words in our vocabulary, right? Now the maximum likelihood estimate for this model will say phi of k, where k is the word in the vocabulary, is given by this term, where you're summing over every message, and within each message you're summing over every word and counting only those words in those messages which happen to be k and belong to the class that we are interested in, and divided by the total number of words across all messages in that class. And similarly, phi of k given y equals 0 equals basically the same thing, just replace y equals 1 by y equals 0. Right? And you can also have a Laplace smoothed version of this. I'm going to write out the Laplace smooth version and then give some more intuitions about this. Phi k given y equals 1 plus I equals 1 to n, j equals 1 to di, x I j equals k, and yi equals 1 divided by the vocabulary size plus right. So this is the similarly you have a phi k given y equals 0 equals a similar thing, just replace y equals 1 with 0. And the way to think about these, the Bernoulli event model and the multinomial event model is to probably look at how an algorithmic implementation of these two models would look like. Right? So supposing we have a training set, let's call this, buy our lottery and whatever, buy this watch, right? You have a few examples, and let's say you also have a non-spammy example. For example, when is your exam? When is the homework due? Right? Now, first let's look at the Bernoulli. So in the Bernoulli, we convert this into a fixed length vector where we have a aardvark by exam and so on. And what we do is for each example we use an indicator variable to say whether the word appear or not. Right? Similarly here, it's going to be a buy, and there's going to be a watch, and zeros everywhere. Right? So this is the fixed length representation, which is d-dimensional, where d is the size of your dictionary. So the way you want to think about this is, in case of the Bernoulli model, first we're going to convert a given message into a multi-hot vector, which means it is 1 in multiple places. The word may appear many times in a given message, but we count it only once, right? So maybe to clarify this, buy this watch only, right? And we do this, repeat the same thing for the non-spammy. So here we will have, exam will be 1, your will be 1, the others will be 0. And similarly, this will be a few places. Right? So we have a set of spammy examples and a set of non-spammy examples. Right? And for each of these two different classes, we have a separate collection of Bernoullis per word. So we have one Bernoulli for the word A, one Bernoulli for the word aardvark, one Bernoulli for the word buy, and each of these Bernoullis is estimated by summing over the number of times the word has a 1 divided by the number of words in that class. Similarly over here, another set of Bernoulli. So this is 5 5j for y equals 1. This is 5j for y equals 0. And each of these 5j's, you just count the fraction of words, the fraction of messages in which the word appears divided by the number of messages. And similarly, the fraction here, this will be 1 over 2, this will be 2 over 2, and so on. Right? This is the Bernoulli model that we discussed first. Right? And similarly, the multinomial, however, is a little different. The multinomial, right, if you were to implement this algorithmically, right, assume you have the same set of words here, a, aardvark, by, exam, and so on. In this case, however, instead of using an indicator, just count the number of times the word appears. Right? So 0, 0, by is 1, lottery is 1. Over here again, by is 1, watch is 2. So if this is watch was 0 here, only is 1, whatever. Right? And now we do the same normalization by summing up the counts. So the number of times the word appeared across all examples in your training set. Right? Whereas over here it was the number of messages or number of examples in which the word appeared. Here it is the number of times the word appeared across all messages. Right? That's the main difference between the Bernoulli model and the multinomial model. And so here so we're going to sum up the counts. So here it's going to be 2, 2, 2, and maybe some of them it is 3, it is 4. In the Bernoulli model, each one of them was its own Bernoulli variable. So we normalized it locally. Right? In the multinomial model, we want a distribution over words. So we're going to normalize this entire thing by summing over 4 plus 2 plus 3 plus 2 plus 2. Right? So the multinomial model gives us a distribution over words of how frequently that word appears in spammy messages or non-spammy messages. And it doesn't care about whether the word appears 1,000 times in one message or appears once in 1,000 different messages. The multinomial model doesn't care. The Bernoulli model, however, counts what fraction of the messages has this word. The Bernoulli model cares, it doesn't care how many times the word appeared in a message, it's just going to count it once per word, once per message. Right? And when you apply Laplace smoothing, what it basically does is you add two messages. One message has 0 everywhere, and one message has 1 everywhere. Right? And then renormalize it locally, you get the Laplace smooth version of the Bernoulli event model. Similarly, you extend the zeros here, one message that has no words and one message that has all the words, and renormalize it, you get the Laplace smooth version of the multinomial event model. Any questions? Yes, question.
If the design is with some word and you put like 10,000 instances of that one word in that message and no other spam has that word,
yes,
will it throw this off because it will assume it will distribute it over the entire distribution?
So the question is, if there is one spammy message that has a spammy word repeated 10,000 times but does not appear in any other message, then this model will upweight that word by quite a lot. This model will think that there's just one message with that word. That's the main difference.
So should that weigh the number of spams it appears in? So like if a word appears in 10 different spams, we should weigh it by that we keep track of.
So in this model, it is just summing up the words. So one way to think about this model is take all your spammy messages, concatenate it into one long example, you get the same model. Even if you have one message, that's a concatenation of all your messages. Whereas with this, you're counting how many number of messages a word appears. Right? That's the main difference between the two. Yes, question. Yes.
So here, if you said that when the Laplace smoothing happens, we have two examples of zeros and ones.
Exactly.
So wouldn't it add only denominator to one?
Here you're only summing up, right? So only the second one will sum up plus v. Right? When you add up all these, you're getting zeros over here, and here you're getting 1 per word. So that's what gives you the plus v. So the Laplace smooth version, we have a plus, we're adding the number, the vocabulary size to the denominator, right? And that is basically achieved because you're adding a +1 per word. So there are, v such words, and when you sum up, when you sum up all the counts here, you get a plus v in the denominator. So the Laplace smooth version of by will be, in this case, 2 plus 1, 3 over the original count, whatever it was, plus v. Right? It's going to be, this is 2 plus 1. So without Laplace smoothing, it was 2 plus the original count. Now it's going to be 2 plus 1, because you got 1 from the new message, and plus v in the denominator because every word got 1. Sum of all the words. You're summing over all the number of words, right? So over here, you're summing over the number of words in your spam class or the number of words in your non-spam class. Yes, question?
If I trust them who you added to the Laplace smoothing for the first example, and shouldn't be one negative sample with all words 1 instead of one positive sample with all words 0?
I don't think.
Yeah, I mean those two extra samples you added for the Laplace smoothing for Bernoulli distribution.
Yeah, so the idea is, these counts may all be ones or all be zeros, and you don't want them to dominate, so you add a 0 and a 1 for each word.
Okay, but as the formula suggests, it should be one positive sample with every word and another negative sample with every word instead of a positive sample with no words.
So with Laplace smoothing, we add 1 positive and 1 negative per word. 1 positive and 1 negative per word. All right, I think we're over time, so that's about it. If you have any more questions, feel free to walk up and I can answer them.